This is question 2 from the SACE Stage 2 Physics course companion from chapter 3.3, Structure of the Atom. Here we have an electron energy level diagram for an atom. First, we need to calculate the highest possible energy and wavelength of a photon that may be emitted from this atom. Now this is fairly straightforward. If we're trying to determine the maximum possible energy, that's just the energy corresponding to the n equals 1 level. So here the maximum energy is just 19.21 electron volts, or we can convert that into joules simply by multiplying by the charge of an electron, which gives us 3.07 times 10 to the power of minus 18 joules. Next, we need to calculate the frequency of a photon that is the result of a transition from n equals 4 down to n equals 2. So again, this is fairly straightforward as well. Here we need to work out the energy of the photon. It's just going to be the energy corresponding to the energy difference between the electron energy levels. So here, if we're going from 4 to 2, it will be 10.76 minus 2.08 electron volts, and so that'll end up being 8.68 electron volts, which we can convert to joules in the same way. I'm just going to do the calculation rather than showing the working for every single one, and this will end up being 1.34 times 10 to the power of minus 18 joules. Now we have to work out the frequency of that photon. So here we know that E equals HF, therefore F will be equal to E on H. We have the energy from just before, so 1.34 times 10 to the power of minus 18 divided by H, which is Planck's constant, so 6.63 times 10 to the minus 34. And if we substitute that into our calculator, we get 2.09 times 10 to the power of 15 hertz. So that's fairly straightforward. Part C, we're determining the wavelength of a photon that's emitted from when it transitions from n equals 2 to n equals 1. It's the similar sort of process to what we've just done. We need to first work out the energy of the photon, so that will be 19.21 minus 10.76, so 19.21 take 10.76 electron volts, which happens to be 8.45 electron volts, which if we convert to joules by multiplying by the charge of an electron, we get 1.35 times 10 to the power of minus 18 joules. Now we have to work out the wavelength. So we start off with our expression for the energy of the photon, E equals HF. Since we know that C equals F lambda, we can substitute in for the frequency C on lambda. Therefore, E equals HC on lambda. Rearranging gives lambda equals HC on E. And now we just substitute the values that we've got. So Planck's constant, 6.63 times 10 to the power of minus 34, multiplied by the speed of light, all over the energy that we've just calculated, 1.35 times 10 to the power of minus 18. And if we substitute that into our calculator, we should get 1.47 times 10 to the power of minus 7 meters. Finally, part D, we need to work out the ionization energy of the atom. The ionization energy is just the minimum energy required to liberate an electron. So here it's just the energy equal to the ground state essentially. So here if we supply an electron with 19.21 electron volts, it's sufficient to just liberate it from the atom So here, that 2 will just be 19.21 electron volts. So that question wasn't too bad. It's just a lot of conversions, and the hardest part of this, I think, was substituting C equals F lambda into E equals HF, but even that wasn't too bad. The calculation's fairly straightforward. The conversions are fairly easy. It's a fairly routine, simple sort of question.